departmental physics colloquium. And this is the kickoff to our 2021-2022 series. I'm very much looking forward to today's talk by Henriette Elvang. And I just want to welcome you to and remind you that this is a weekly occasion, and our colloquium series will be a bit of a hybrid this year. We're hoping to transition to in-person talks later in fall and increasingly so in the winter. So pay attention to the schedule and to any announcements, and please stay and enjoy and engage in this great series. So with that, I'd like to pass the baton to today's host, who's David Curtin. Go ahead, David.
Thanks, Paul. So hi, everybody. So it's my great pleasure to introduce Professor Henriette Elvang from the University of Michigan. She'll be giving our semester's inaugural colloquium. Henriette is an Arthur F. Thurneau professor at the University of Michigan. She came to the States from the University of Copenhagen to do her PhD at Santa Barbara. And then she joined Michigan after postdoctoral positions at the IIS in Princeton and MIT. Henriette is a leader in the study of fundamental properties of quantum field theories in GR, general relativity, and she's a fellow of the American Physical Society and a recipient of numerous honors. So we're very happy and honored to have her with us today. Henriette, I'm going to hand this over to you. I just want to tell all the attendees that Henriette likes to give lively talks, so please interrupt with questions at any time. Now, when I say interrupt with questions, what I really mean, due to the restrictions of the format, is enter your questions into the Q&A panel, and I will relay them to Henriette in real time during the talk as much as possible. And then at the end of the talk, we'll have a Q&A where I will unmute attendees and you can ask your questions by audio as well. Okay, Henriette, it's all yours. Take it away.
Thank you, David, and thank you so much to both David and Paul and all of you for the invitation to come to Toronto. I wish it could be in person, but I'm also very happy to be here for your colloquium. So the talk today combines two different main subjects, and so let me present each of them. So on the front hand, when I mentioned scattering amplitudes in my title, your thoughts are probably drawn to particle physics. And so here I'm illustrating with an example from the LHC where protons smash together and spray out a new set of particles. The particles, charged, may leave tracks in the tracking chambers, deposit energy in the calorimeters, and based on that, the event can be reconstructed by particle experimentalists. The theory that they can compare with then quantum field theory calculation of the scattering cross-section that tells us about the probability of a given process to happen as a function of energies and scattering angles. On the other hand, we have gravitational physics, and one aspect of gravitational physics is gravitational waves, as predicted by Einstein's general relativity. So here, there's a picture, an artist's impression of an in-spiral of two objects. So think of those maybe as black holes or neutron stars that are going around of each other. And as they go, they lose energy, and they get closer and closer until they may be coming together and forming perhaps one big black hole. As they spiral in, the energy that is lost generates gravitational waves that are ripples in the fabric of space-time that travel out and eventually hit the LIGO detector where they have been detected. So when we describe these two subjects, one is particle physics taking place in high energy collisions, small scale. The other one is large scale astronomical objects and astronomical scales. At first, it may appear that these things don't have so much to do with each other, but what I'll show you is that not only can we use amplitudes in both contexts, scattering amplitudes, to describe the physical phenomena, but these physical objects, the amplitudes for the gravitational problem and the amplitudes for the particle physics problem, are intimately related to each other. And that will be one of the main messages in the talk, that things that look like particle physics and things that look like gravitational physics are actually very closely related. So let's start on the side of particle physics. And again, feel free to ask questions, and I think David will then read them out. Okay, good. So let's think about colliding protons at CERN. We smash them together, new particles are created. Let's zoom in on that. The protons consist of quarks. Quarks are massive spin 1/2 fermions. the up quarks that have electric charge plus 2/3 and down quarks with electric charge minus 1/3. Together, we say that a proton are made of 2 ups and 1 down, giving it a total plus 1 charge. And so we have now this picture of 2 protons interacting. But really, we should think about each proton being some sort of quantum soup of quarks and antiquarks of gluon with a net of 2 up quarks and 1 down quark. And so when the protons interact with each other at the LHC, there are actually these partons inside that are interacting with each other. Now, I mentioned the quarks already. The gluons are massless spin 1 bosons, just like the photon is a spin 1 boson. But unlike the photons, the gluons are interacting among themselves. And all that is described in quantum chromodynamics, what we often refer to as the theory of the strong nuclear force. All right, so what actually happens as we collide 2 protons at high energies? Perhaps what happens in many cases, what can happen in many cases, is that 2 of the gluons interact. They could, of course, also have been quarks or antiquarks, but gluons could interact with each other. And let's suppose that out of the scattering process, 2 other gluons emerge at some scattering angle between. These gluons hadronize, and they create the jets that are then seen in the detector, and as in this dijet event here. All right, let's zoom in again and say more schematically what is going on. I have 2 gluons coming in, and I have 2 gluons going out. I'm looking at this in the center of mass frame, so these gluons come out back to back, but they may not come out in the same direction as they came in, so there's a scattering angle that I call theta here. The probability of this process is encoded in the differential scattering cross-section that gives the probability of this happening as a function of the energy momentum, in this case, for example, the center of mass energy in the process, as well as the scattering angle. In this simple example, there's just 1. And this differential cross-section is what you can go out and measure in using the detectors. Theoretically, the scattering cross-section arises as a sort of phase space integral over an amplitude absolute value squared. So this is reminiscent of our quantum mechanics, where probabilities are calculated from absolute value squared or wave functions. But in this case here, we have a phase space integral, and it's the object that plays the role of the wave function in a quantum field theory context is the amplitude. It's a different object, but it has the sort of the same analogs. Now, the scattering amplitude can be computed traditionally as sums of Feynman rules. And QCD tells us that gluons self-interact, as I mentioned, and they self-interact with 2 different types of Feynman vertices, one that is cubic and one that is quartic. And so the Feynman rules for computing amplitudes is that you have to write down all the possible diagrams for the process. And you organize them in perturbation theory, where you're expanding in small couplings in such a way that the diagrams that have no internal loops, they're called tree diagrams, are the leading order contributions. And then every time you add a loop to a diagram, that will give higher powers on the coupling, and therefore those loops correspond to quantum corrections. And so this is a perturbation series organized in the power of a small coupling. Now for QCD, QCD famously is strongly coupled at low energies. So when we talk about parton scattering, we're thinking about high enough energies where QCD has this asymptotic freedom. That means the coupling that runs with energy scale is actually small, and we can think about this as a perturbative expansion. So I'm thinking here, high energy, where partons make sense, and I can study this problem. Okay, so this is how you traditionally do it. And each diagram that you see here is maybe about a line or so of algebra written in UNICE's textbook form. So then you add these diagrams and you simplify it a little bit. Now, in a standard QFT class, quantum field theory class, you might learn to calculate this 2-to-2 process. It has 4 diagrams, but you probably won't be asked in any homework or for students' exam problems, you might not be asked to calculate the gluon, 2 gluons coming in and 3 gluons coming out. That has 25 diagrams, and that maybe be a little bit too much to do. But of course, a computer can do it. When you go up in number of particles involved, the number of diagrams explode. And it's not so hard to see why, because at every one diagram I have a 4-point, the number of places I can attach another line. So basically think about radiating off another gluon. There's numerous ways I can do it. I can attach it to a vertex to make it quartic. I can attach it to one of the other lines. So there are many, many different diagrams, and that's why these numbers end up exploding as the number of particles involved in the process increases. And remember, this is only the leading process to the scattering of gluons. This is the leading tree-level order. If you're including loops, this explodes way more. Now, that means Feynman diagrams quickly become intractable. Of course, I can always get a computer to generate this, but what am I going to do with the result of the sum of 30,000 diagrams? Yet, surprisingly, it turns out that one can prove that many of these amplitudes are extremely simple, in particular, one class of them that I'll now describe. So I mentioned that gluons are massless spin 1 particle. You can characterize them with a property that's called helicity, which basically states whether the spin of the particle points in the direction that it's going, the same direction as its momentum, or in the opposite direction, and we call that positive and negative helicity. If I specialize to the type of process where I have 2 positive helicity gluons coming in, and n minus 1, so it's a total number of n particles, so I have a whole lot of only positive helicity gluons coming out, then the amplitude takes a remarkably simple form. It's just that. So for this n number of gluons involved being 8, this one single term makes up for the entire set of diagrams here. Well, that's almost true because I did a little bit of color ordering, but essentially you get the point that this corresponds to thousands, or sum of thousands of diagrams. It's written in a so-called spinor helicity formalism that I won't use in this talk, but I just wanted to mention it. It has these angle brackets, and then angle bracket is basically the same as a square root of the product of the 4 momentum of each of the 2 particles I and j. And then there's a complex phase, but that's essentially what it is. This formula is known as the Park-Taylor formula, and it was basically guessed by Park and Taylor in the mid-80s and later derived. So what goes to say is that even though the Feynman diagrams indicate that these expressions should be infinitely complicated almost, the actual answer turns out to sometimes be remarkably simple. So up through this result and up through the 90s, a lot of new methods were developed to efficiently compute amplitudes, especially amplitudes relevant for particle phenomenology that include tiny departure scattering, such as the gluon scattering we've just discussed now. Also, the weak force carriers, the W and C boson, production of those. Of course, Higgs amplitudes, because of course back then we hadn't yet observed the Higgs, and so on. So one set of relations are known as the Baron-Schiele recursion relations, and they were in fact used to actually prove that this result is correct. It's still one of the fastest methods to compute parts and amplitudes. And then Baron, Dixon, Kossover, and collaborators, they began to develop a large set of methods that was in part inspired by string theory, but also by generalizing the standard unitarity methods that you learn about, and sort of generalizations of Fermi's golden rule. Now, this includes sometimes the use of supersymmetry to organize the calculations. They realized that in theories with a lot of supersymmetry, so that's a very special symmetry that relates bosons and fermions, when you have a lot of that amount of supersymmetry, you have a lot of control over the theory that you might not have in a setting like QCD. That allows a good testing lab, so to speak, for developing new methods. Once you have new methods, then you can go ahead and apply them in other contexts. And so that was a very useful aspect for research in the 90s and going forward. But even though the methods were very powerful for calculating things that were nearly impossible or fully impossible with Feynman diagrams, especially at loop level, then the answer to why are the amplitudes so simple when Feynman calculations make them appear so complicated was not really answered. So what happened in 2003 was a new approach started, a sort of a little bit of an Amplitudes revolution took place. And that Edward Witten wrote a paper where he conjectured a new formalism for gluon amplitudes that were based on twistor string theory. So twistors were invented by Penrose. Maybe they look like a mathematical curiosity, but in Witten's approach, you got some compact integral expressions for these gluon amplitudes that encoded the thousands of diagrams that would have been needed from a Feynman perspective. So Zvi Baron recently gave a retrospective review of amplitudes at the annual Amplitude conference here in August. And he mentioned this paper, and he said that Witten's paper landed as a meteorite, sending shockwaves even to this day. So that gives you a little perspective on the impact this paper had. We won't need the details of it, but it was sort of to give a little bit of the history of the subject. Now, in 2003, I was in grad school, and I was in Santa Barbara and at UCSB, and there was a conference at the KITP where indeed Witten presented this work. And so it was clear, I could feel the shock waves. I was moved by those shock waves from the meteorite paper landing. And I could see how the postdocs and David Gross and other people got extremely excited about Nielsen approach, and then basically a lot of them started working on it right away. But I was busy with other research things. I was interested in black holes, and I had just found some new solutions that are called black rings, that are donut-shaped black holes. I was interested in charges and how they fit into string theory. And so I sort of just didn't catch on to this whole amplitude frenzy that was going on around me. I sensed the excitement, but I didn't catch on. Not until a few years later. So for a few years after 2003, there was a huge amount of work done on amplitudes, the twistor approach and generalizations thereof. And then there was a little bit of a slow point, and then it started really picking up again in 2007. In fact, I was so busy with my rings and stuff, and one of the things I was also busy with was that I was very lucky to be able to visit in Toronto when you guys hosted Strings 2005, and that was really a wonderful experience. And now reviewing the poster from that conference, I'm so happy to see that you have black rings in there too. Okay, so what changed for me in 2007 when I started working on amplitudes? There was a paper that came out at the end of 2006, which with a very provocative title, which is N equals 8 supergravity ultraviolet finite. So let me try to explain the context of this. Already in the abstract of the paper, you can see the statement that conventional wisdom holds that no four-dimensional gravity field theory can be ultraviolet finite. Okay, so let's translate. What happens when you have gravity is that, or in any of these kind of field theories that we're going to talk about, is that we talked about organizing the perturbative expansion into tree level and loops. Now, even in QCD and in quantum electrodynamics, which is the quantization of Maxwell theory in E&M, we encounter divergences when we compute the loops. You have to compute certain integrals, and sometimes they have divergences. These divergences have to be regulated, and we have a procedure for doing this that's called renormalization. It works great for quantum electrodynamics. It works great for quantum chromodynamics. These are renormalizable theories. But it does not work great for gravity. And I'm going to tell you more about what I mean by calculating gravity amplitudes later. But it doesn't work in the sense that you can't absorb these divergences in any sort of predictive way. This is one of the motivations for string theory, because that regulates the theory by having a finite extent of the string. But as a field theory on its own, gravity doesn't seem to do very well, because it loses its predictive power at loop level. But what Baron and Dixon and Roybal here proposed was perhaps when you have this symmetry between bosons and fermions that can run inside the loop of the gravitational loop amplitudes, and the couplings are related because of this additional symmetry, perhaps there can be cancellation that happens that eliminate the divergences that we know otherwise. And those cancellations happen. And one of the motivations for this papers were a number of observations seen in explicit calculations, as well as the fact that these authors and their collaborators had shown that the free loop for graviton amplitude was indeed UV finite. So there is no need for renormalize. Okay, so cutting it all short, what were they proposing? They were proposing that if you have enough supersymmetry, then perhaps there's no need for renormalization. Perhaps there is some other version of quantum gravity that makes sense outside the regime of string theory. So that piqued my interest because it seemed that extremely little was known about what is even allowed based on the symmetries of this theory. But what could I do to learn about this problem? Well, I couldn't do for loop calculations. I would have been left in the dust by the experts for sure. I wouldn't have a chance to start this. So there was no way I could have competed with anybody trying to do the next order calculation. So instead, I started from scratch, and I went back to try to figure out what is gravity amplitudes even. And so let's talk about what are gravity amplitudes and what can we learn about them. Okay, So just like electromagnetism is a force that's mediated by the photon, who's a massless spin 1 particle, and we've talked about the strong force QCD has massless spin 1 particles that we call gluons. Gravity has massless particles that are called gravitons, and the difference just here is that they're spin 2 and not spin 1. What do I mean by gravity? What I mean is Einstein's theory of general relativity. And as we know it, it is described by Einstein's equation. And the standard words that go along with here is that Einstein's equation, matter tells space-time how to bend, and the bending of space-time tells matter how to move. So it really has that nice geometric feature. Now, Einstein's equation is really an equation of motion that you can derive from a variational principle, just like you learn in your Lagrangian mechanics. So the action or the Lagrangian that you use to derive this equation of motion that is Einstein's equation from is called the Einstein-Hilbert action. And it takes this form here. So it involves Newton's constant G. It involves the metric, and the curvature of space-time. And the space-time curvature is a function of the metric that describes your measure of distances in potentially curved space-time. And this here is the square root of minus the determinant of that metric. Okay, now let's think about Newton's constant to begin with. Newton's constant, if we think about it in units where the speed of light and h bar are set to 1, then G is basically related to, it's basically the same as the Planck mass. So the Planck mass is the square root of 1 over, so it is 1 over the square root of G. And that comes out to be about 10 to the 19 GeV. For comparison, LHC collisions happen about 10 to the 4 GeV. Okay. So what does it mean that we're doing perturbative gravity? What are these perturbative calculations we're talking about when we talk about graviton scattering and a 4-graviton amplitudes? Well, that comes about as follows. Suppose I take my metric and I expand it around flat space. So I imagine that I have flat space and I'm just looking at tiny fluctuations, and those fluctuations are given by h mu nu here. The kappa that sits here is practically the square root of G. So that will be the coupling that involved here. So when I take my Einstein-Hilbert action and I plug in my metric, so I look at these small fluctuations around flat space, the leading term I get is quadratic in h. And if I just forget about anything else that comes out, the equation of motion that arises from this, when you do a certain gauge fixing as you must, is basically the wave equation that describes gravitational waves, namely the fluctuations in space-time. So this is where gravitational waves come from. You can see directly how that follows from this part. And of course, famously, gravitational waves are real. They've been detected by LIGO. The first event is now 6 years ago. I can't believe it's 6 years already, 6 years ago in 2 days, and was announced in February 2016 and very quickly led to the Nobel Prize to those who proposed LIGO, Rainer Weiss and Barry Barish and Kip Thorne. All right, but we can't just stop at the leading order and the expansion. We have to see what else is there. And as you go up in order, and I'm sorry, here there should be higher powers of kappa that will be on the coming slides. But here you see that this term here, in a context of particle physics language, what used to be our gravitational wave term is now basically the propagator. And that makes sense, that's the propagator of the graviton. The h cubed field is a cubic interaction, h to the 4 is a quartic interaction, h to the 5 is a quintic interaction, and so on. This expansion goes on to endpoint any number of particles that you need. And all of them involve two derivatives. And here I've written it very schematically, but you can imagine that all these indices that sit on the fields and the derivative get contracted into each other in very complicated ways. In fact, it is very complicated. If I start writing down what the Feynman rules are that you would get out of these terms here, for a 4-particle amplitude, as Shannon did in '86, you get something that looks like this. So here is the first diagram. And if you compute what it is, you find that it is this whole mess. The E's are polarizations of the gravitons, the K's are their momenta. And this goes on with about, for just the first diagram, about 3 times as many terms as I've shown here. And similarly for diagram B and C and D, each of them is about a page in a paper of that sort of stuff there that you probably didn't want to see. But it's there. And so our perception might be that this is increasingly complicated. Of course, one thing I will tell you, it's not as bad as it looks, but we'll get there. Let's just talk about whether we even care about graviton scattering. So if I look at my action here, then I have, then I see here that I have my Addison-Hilbert action. We expanded it out. Now I have the couplings, right? And that the expansion is controlled by a dimensionful quantity, which is kappa. But when we talk about a coupling being small, we have to talk about small compared to what. And the compared to what has to be compared to the characteristic energy in the scattering problem. So if we're thinking about two particles coming in and particles going out, the natural thing to think about there is the center of mass energy, E. And so that is the characteristic energy of the process. And so when we talk about perturbation theory, it should be in a dimensional coupling that is the center of mass energy times kappa. But remember now that kappa was 10 to the minus 19 GeV inverse. And so even for the very high energies at the LHC, which are of order 10 to the 4 GeV, the effective coupling is of order 10 to the minus 15. And that's, of course, extremely small. So we immediately conclude that for LHC processes, there is no way that these gravitational self-interactions play any role. So why do we care? Why am I talking about this? Of course, there has to be a point. Well, the point that you could keep in mind is the following. When we talk about tree-level processes, including these ones here, like this 4-point scattering, what we're really talking about is a different perturbative way of encoding of classical physics. So tree-level is encoding the classical physics, and loops encode the quantum corrections. So somehow, perturbatively, tree-level scattering has to capture the same classical physics that was in Einstein's equations. And we know that Einstein's equations include things like Schwarzschild solution, black holes, description of geodesics around massive objects in the sun, and so on. We know that that is there, and so there has to be a role where gravity plays a role. Of course, it has to be there. We use it every day. But then how does it come in? So why do we care about the gravitational scattering? There's the equivalence principle that in a particle physics language says that gravitons must interact with all other matter with the self-coupling as it does with itself. So the logic behind this is gravity is something we know or familiar with. It attracts masses to each other, but mass by E equals mc squared is the same as energy. So anything with energy has to interact gravitationally. Anything with mass, everything with energy must interact with each other gravitational, and it must do so with the same universal coupling, which in a perturbative context is kappa. So imagine that I have two massive objects. I have a mass m1 and I have a mass m2. If I exchange a graviton, it has to be with coupling kappa. And so this particular diagram here for, say, a scalar particle of mass m1 and a scalar particle of mass m2, exchanging a single graviton, is something that gives order kappa squared, which is g. So this is something of order Newton's constant. If you take this amplitude that I just wrote, and you take a non-relativistic limit of it, and you Fourier transform it from momentum space into position space, you find that the effective potential that describes exactly this one graviton exchange is exactly Newton's potential, minus g m1 times m2 over the distance between the two objects. So we recovered from the scattering process of a very simple tree-level diagram, clearly classical physics, our classical Newtonian potential. Now there are two kinds of corrections to this. There's the first thing is here that this is really like electrostatics, right? These two masses are sitting at rest. But what happens when they're moving around each other with some relative speed v? Then when they're moving masses, we can think about corrections to this result in non-relativistic expansion and small relative velocities v over c. Why is it non-relativistic? Well, think about black hole and spirals. These are huge objects out on astronomical scales. They're not going at speed near c. They're going at some, maybe fast, but it's a sensible thing to expand them in small v over c. And that is called the post-Newtonian expansion. Now, there's also an expansion you can imagine in powers of g. Where does that come from? That would come if instead of exchanging just one graviton, suppose I exchange two. Then for every vertex I have in the story, I must have a factor of kappa. And so all of a sudden I have 4 factors of kappa instead of just 2. That gives me a contribution that is order g squared. And so, as we'll talk more about, there are higher powers in G that enter, and those are often referred to as Postman-Kovskian corrections.
Henriette?
Now, yes.
Sorry to interrupt. There's a question in the chat by Ephraim Steinberg. He asks, I'm confused by this connection between tree-level and classical. Tree-level QED doesn't give you only classical ENM. We still have spread-out electron clouds or single photon or squeezed states, all sort of quantum stuff without loops. Wouldn't quantum gravity already be interesting at tree level? How does a wave packet gravitate, etc.?
Good. So I think maybe one thing I can say comparing this to QED is if I had drawn the same diagram and instead of calling them N1 and N2, call them charge 1 and charge 2 and have them exchange the photon, then the same procedure that takes me to the gravitational potential here would have given me the Coulomb potential. So that's really just the same calculation in a different context. So maybe it's a good question also to discuss later. But if I talk about quantum gravity, I think it's probably the context here is perturbative gravity, that just like perturbative QED is relevant also classically, and quantum corrections are important. Quantum corrections could also be calculated here, but it turns out to play a little bit of a different role. But maybe we can take that question up again at the end, if that's okay. And I can try to understand it better. Is that okay?
That sounds great.
Okay. All right. So here in the context of black hole and spiral, it turns out that a sensible expansion has the non-relativistic expansion in small v over c. Here just left in units of c equals 1. So in that case, v squared is of the same order as g times m over r. And m here being the total mass of the binary system, g the Newtonian constant, and r the separation. Both are small quantities in this context, and they are roughly of the same order. So that means that when we take into account that the objects are moving, then and expanding in v over c, we must at the same time also, to be consistent, compute the Postman-Kovskian powers in g. And so that is what they do, and in particular, one paper I will refer to is the one by Baron and Chung, Roy Banschen, and Solon, who makes this story very clear. In fact, here's a table where they set up to illustrate this. On the horizontal axis, you see the post-Newtonian orders. That's the expansion in V. C is set to 1. And these are done at 1 p.m., so that one Postman-Kovskian order, that's just the gravitational powers in Newton's constant to the first power. And then there are 2 PMs, and then of course that expansion that corresponds to the same thing. If I have 2 factors of G, that corresponds to having no factors of V. And so this organizes very well the calculation for the binary in spirals. And in particular, a paper by these authors and some certain subsets of them calculated for the first time the 3 Postman-Kovskian order here. So that's why that is indicated in red from their paper. Are there more questions, David? I see there are more chat messages.
No, it's all good.
Okay, all right. So we have this, and so the statement here is now the following. Let's summarize that higher powers in G are important. The leading order exchange gives us the usual Newton potential. If I exchange 2 gravitons, or I let the gravitons interact in this way here, all in all, I have 4 powers of kappa, 1 for every vertex I have. And that will give me order G squared corrections. Some of those were calculating systematically by Donahue early and with some additional contributions from Bjørn Bohr and others later. And you can just sort of see how they calculate every one of these diagrams and then finally put it together in one big contribution of order G squared at the end. Now I could go to 1 order higher, and this would be the orders that were computed here for that purple line, namely the 3rd Postman-Kovskian order. And so I could have changed 3 gravitons, or I can look at the self-interactions among the gravitons, all of which in these diagrams I would calculate to have 6 powers of kappa. So that means it's order G cubed. And of course, there are many other diagrams I could have here. Now, if I just look at the things I've circled here in red, those are exactly the self-graviton diagrams. So if I somehow made a cut, which is a unitarity methods approach to computing these diagrams, I could make cuts that separate off these parts. And now we see that graviton self-interactions are directly relevant to know for these type of computation. So they really answer what is in the red box, a red circle here, are directly the graviton amplitudes with just its self interactions now stuck on to the massive lines. But graviton scattering now is something we care about, but it does sound a little bit complicated, right? It's like all these complicated diagrams with polarizations and dotted into polarizations and momenta and so on. Doesn't sound much fun to work with, and I'm sure it wasn't much fun for Shannon to do back in the 80s. He spent an entire paper calculating this 4-point amplitude and simplifying it.
Henriette,
yes.
Sorry, there's another quick question from the audience.
Yes.
So the question is, when you have such high corrections in higher powers of G, are we changing the power of Newton's law, question mark? So in other words, the question is, do the extra powers of G change the power of R in the potential?
Good. Some of them do. So for example, in Donahue and Bjorn Bohr, you will see terms that are 1 over, I think 1 over R cubed comes in, or 1 over R squared comes in with different powers of G. But there are also different types of contributions that enter. That's correct.
Great, thank you.
Great. Okay, so very good. So this looks extremely complicated, but it turns out that once you simplify it, and Shannon's whole purpose of this paper of computing this was indeed to do that, and you find something remarkably simple, namely that the 4 graviton amplitude at tree level is nothing but a product of 2 gluon amplitudes. And I'll come back to what these numbers mean here. They're organized a little bit differently. I'll show you soon what that means. But it's practically a product of 2 gluon amplitudes that we started out talking about, times something that we call the Mandelstam variable. I denote it here S. It's basically for a process where particles 1 and 2 are coming in. This is essentially the center of mass energy squared. Okay, so you have something like this. And that looks really crazy because the Feynman diagrams were so complicated from the point of view of gravity. And while Yang-Mills is a little bit more complicated than QED, it's not too terrible to calculate these processes. And I showed you also that these two Yang-Mills this Yang-Mills process at 4-point could be given by simply this Park-Taylor formula that was like a 1 compact term expression. That also means that the 4 graviton amplitude is a 1 compact term expression. So all of this Feynman rule mess simplifies to just an extremely simple expression. And this is an example of something that is now known as the double copy. It has been known actually as about as long as the Park-Taylor formula, but in very different contexts. And I'll talk about it in a very different way that it was known in the late 80s. So this is not just a miracle that happens at 4-point that this reduces, but in fact, it happens also for any number of external particles at tree level. There's a similar formula. It's not just one S that sits there. It's a more complicated structure, but it does exist. So the double copy says somehow that gravity at tree level is the same as Yang-Mills squared. Now, this is the way, or the slogan that this is always presented by. It's a tiny bit misleading because, as we'll see, the role of these kinematic factors that sit there are extremely important. But the sense that Yang-Mills product with Yang-Mills with a certain sense of what product means gives gravity at tree level for the amplitudes, that is true. And this has many applications. It was allowing people to explore this UV structure of supergravity theories, and UV finiteness that I mentioned was one of the provocative results that got me into the field in the first place. It has been used in these calculations by Baron and collaborators for gravitational in spiral effective potentials relevant for the gravitational radiation problem at 3 post-Minkowskian order. In fact, they just sort of chop up the diagrams and use this double copy to compute each piece and then glue them back together. It's been used to say, well, if gravity at classical gravity is the perturbative tree-level expansion, and this holds for the perturbative tree-level expansion, maybe something similar holds for solutions to the equations of motion, and that has been explored now by people from the field of classical gravity who study Einstein's equations a lot more in various contexts. It's been an interesting property to study for string amplitudes. In fact, this relation originally came from string theory, as I'll mention a little bit more about. And then a funny feature is that this also holds for what is known as chiral perturbation theory. This is the low energy effective field theory that can be used to describe pions. And you can double copy pi into themselves and get something that are called Galileans, which are some funny scalar particles that people in cosmology tend to like. And then there are various generalizations to anti de Sitter space and so on that people are studying now. So this has become a huge area that people are studying. Now, recall that I was originally busy with black rings and stuff when the first meteorite of amplitudes hit. But in 2007, my first amplitudes paper was in fact studying this relation. We were curious because the standard formula for amplitudes didn't exactly square the Yang-Mills amplitudes, the gluon amplitudes, and we found a formula where that happened by changing the kinematic factors in front. Okay, so let's talk about this double copy. How can it even possibly work? So let me just mention that the gluon amplitudes can be color ordered. They come with a color structure, and this is a little technical, but the idea is simple. You basically separate off the kinematics from the group theory. The group theory is a trace of matrices. We don't care about that trace really. All that is left is the kinematic dependence, and that's what we use, and that's the part that we're going to study. So when we write a double copy, we mean that these are actually color ordered. And so what that translates into is that the diagrams that contribute to a color ordered amplitude are the ones in which where you keep the ordering that I list here for the external states cyclically, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and you don't allow any lines to cross. What that means is that for that amplitude that has the label 1, 2, 3, 4, there is going to be poles exactly where you have an internal line. And so when S denotes a P1 P plus P2, the Mandelstam variable, the center of mass type energy, and that means that since I have 1 and 2 coming in here, there's a pole in what we call the S channel. On the other hand, the diagram with 1, 4 coming in, that has the U pole because that corresponds to that kinematic variable U, because that is the type of particle that is exchanged here. And the local term here doesn't have any poles. Similarly, if I exchange 3 and 4, I won't do anything to my S pole, but the U pole, because I exchange 3 and 4, will become a T pole. But this means that when I try to compute that double copy by taking a product of 2 Yang-Mills amplitudes, I invariably get a double pole in S. And that's bad because amplitudes don't have double poles. They can only have simple poles. And in particular, the graviton amplitudes must have simple poles in S and T and U. So how can it possibly be that this product gives the right answer? And the reason is that it had that Mandelstam variable sitting in front, the S. The minus sign doesn't really matter for what we'll talk about. And that thing that sits there in front is called often called the multiplication kernel. And that is what makes the pole structure work. There's a different form of this product that says that if I take the same ordering, 1, 2, 3, 4, and 1, 2, 3, 4, well, if I compare to over here, I'm just doubling that amplitude with itself. So I'm bound to get a double pole in S and a double pole in U. That's not good. And I'm also missing the T pole. But the kernel exactly comes in and fixes that problem. It has a product of S and U that eliminates the double poles in S and U, and it supplies the missing pole. It sounds like almost like building with Lego and trying to make it work. And the fact that it also not only has the right poles, but right factorization on those poles is somehow almost a bit of a miracle. But these two, yes?
Henriette, sorry, there's a question in the chat asking, someone's confused about the kinematics. Are they not in the phase space integral rather than the amplitude? Can you just to clarify?
So when I talk about the amplitude, I'm not doing any phase space integral. So in these expressions, I'm not doing any integrals whatsoever. Does that help? Yeah,
I'm sure. I guess the kinematics here just refers to momentum factors and things like that, right? Just
so when I say kinematics, I simply mean the momentum dependence of the amplitude as encoded through the ST and U variables here.
Can I ask a really quick question?
Yes.
Maybe this is offline, but the rules for the multiplication kernel, is that something that I can just read off the amplitude or?
No. I mean, so that comes. So right now I'm just arguing what it should look like to make the poles work.
Oh, what it should look like, right?
What it should look like. But these formulas are actually what the double copy formulas look like. And they are examples of what are known as KLT formulas that were originally derived by Kawai, Lavelle, and Tai from a strings perspective. And so this is basically the field theory limit of their string result.
Awesome, thank you.
So these are true formulas, but I'm just arguing why they even have a chance of producing the right pole structure, which from the point of view of just multiplying these things together looks like it could go bad. And so I'm focusing in here on the kernel to say that it plays an important role in eliminating double poles from the product of amplitudes, and it also provides missing poles. And then at 5 point and higher, there are similar rules for what the kernel can look like and how it fixes the problem of potential double poles and missing poles. And these formulas do get more complicated at higher points. So now I've given you two different formulas for the same gravitational amplitude. There's only one gravity amplitude, so these two things have to be the same. So if I subtract these two expressions from each other, I get 0, and I can factor out the common factor of the 1, 2, 3, 4 ordering, and then I'm left with a relation between two gluon amplitudes with different orderings. That relation turns out to be true for Yang-Mills theory, because otherwise this wouldn't be true either. But as an example of what is known as a BCJ after Bernd, Johansson, and Carrasco, a BCJ relation at 4 point. There are similar relations that one can get from other orderings and other ways in computing the graviton amplitudes that must all agree. And they're known as the Clichrof relations. They follow actually just from the group kinematics, as well as the BCJ relation I just wrote. And so these are commonly referred to as KK BCJ relations. Now, let me just summarize what we got so far. So there exists a double copy procedure that maps color order tree amplitudes, such as the gluon amplitudes, into the tree amplitudes of another theory, such as graviton amplitudes and general relativity. And in fact, we also get dilitons and actions, but let's not go into that. Now, not all theories can be double copied. They must have some color structure, and those tree amplitudes must satisfy what are known as KK BCJ relations, of which I showed you examples just before at 4 point. So in order to understand if I can double copy two theories and get the amplitudes of another theory, I must have these relations satisfied, because otherwise my double copy map is ambiguous. We know that Yang-Mills amplitudes satisfy these relations. We know that supersymmetrizations of Yang-Mills satisfy these relations. The low energy effective theory of pions, known as chiral perturbation theory, which is an example of a nonlinear sigma model, satisfies these relations. And then there's a funny model called the bi-adjoint scalar model that also satisfies these relations. So actually this multiplication of theories defines a multiplication that you would have counted in I always remind of my first year algebra class in university of products giving something else. So here I have these four types of theories that I mentioned. Yang-Mills times Yang-Mills gives me gravity plus the dilaton axion. If I look at supersymmetrization of it, I get exactly that n equals 8 supergravity theory that people proposed would be finite at loop order. If I do the pion theory together with the Yang-Mills, I can get what is known as a Soborn-Enfeld model. It's a nonlinear electrodynamics that was discovered way, way long back as an attempt to solve the self-energy problem for charged particles. If I double copy chi-pt with n equals 4 super Yang-Mills, then I get this model of supersymmetric Dirac-Born-Enfeld theory. That's a lower effective theory on D-branes and string theory, so totally different subject, apparently. The pions with themselves give something that are called special Galileans that shows up in cosmology and effective brain actions, something called massive gravity, and in various aspects of model building. And then you see something funny. This bi-adjoint scalar model has the funny property that double copy with anything, it gives that anything back. That means, again, thinking back to my first year algebra class in university, that this map has an identity element, and that is this bi-adjoint scalar model. So this is a funny property. And we can summarize it as a KLT algebra, that the identity element, which is this model, multiplied with this multiplication rule defined by the kernel into anything, gives that anything back.
So quick question from the chat, Henriette. AW is asking, is this multiplication table specific to four-dimensional theories?
It's specific to four-dimensional theories in my counting of degrees of freedom, but a lot of this generalizes to D dimensions. There's a similar story. It just wouldn't be for gravity plus dilaton action. It would be gravity plus dilaton plus antisymmetric 2 form, and so on. So the labels go a little bit different from that.
Great, thank you.
And of course, n equals 4 super-Yang-Mills would in 10 dimensions be n equals 1 super-Yang-Mills and so on. It will be a little bit different. Okay, so my recent work, and I just want to mention briefly what we've been doing, is it's been studying more this algebraic structure and try to organize what is really going on in this story. So here's the endpoint form of what the double copy looks like. AL and RLA right are tree-level amplitudes in some theories. SN is the double copy kernel, and AN left times right is the result of the double copy. Basically what was encoded in that table. So we have this algebra from the KLT, and the question we wanted to ask is, what is so special about this kernel here? What else are we allowed to do? Are there other ways that you can multiply amplitudes and generalize the double copy? And so the key idea is that when the multiplication rule is changed, you must also change the identity element and vice versa. And that means the kernel and identity model are uniquely linked. And so if I want to change the kernel, I have to change the identity model. And then I have to make sure that these relations hold too. And basically what that gives is a bootstrap equation that requires that whenever I want to change my identity element, then I'm changing my kernel. Those get uniquely linked to each other. And once I have done that, I must generalize also what are meant by the KK-BCJ relations, because those are the ones that are exactly encoded in these other algebraic relations. And so I'm imagining changing the product, that means changing the identity and changing the rules. And we can then that way construct more general double copy kernels. We can generalize the strings kernel that were discovered by Kawai, Llewellyn, and Tai in the mid-80s. And we can use that to double copy in much more general ways, especially in the context of effective field theories. So this is the paper, and here are the collaborators. Aiden is my 4th year student. Juan Hang is a postdoc in Michigan. Trudy just graduated and is now just starting a postdoc at UC Davis, and Callum graduated last year and is at UCLA. So let me just summarize what I have told you about. We started out with gluon scattering in high-energy collisions, and then went on to discuss post-Minkowskian corrections to binary inspiroeffective Hamiltonian, and notice there what shows up is exactly graviton scattering. That led us to the story about gravity being Yang-Mills squared, and the recent work with my collaborators about this new bootstrap formalism for the double copy that we're continuing to explore. And this algebraic structure, one thing it does is really that it organizes what we had before. Quantum field theory is a huge landscape of many, many different types of theories with very, very different properties. And the double copy map is a funny map that somehow link all these theories together. Some of these theories are nice and renormalizable, like Yang-Mills theory, but it double copies into gravity, which is not renormalizable. And there are other theories like Yang-Mills. It doesn't have any particular properties in terms of rules for the helicities, but it maps with pions into the Born-Infeld model that has a property of electromagnetic duality. That means it has a certain optical helicity conservation for the photons in that model and their nonlinear interactions. So this algebraic structure organizes this map in a different way and tells you what the rules are once you want to try to generalize these models, such as in effective field theory context, add higher order corrections to the low energy expansion. What are the rules for the double copy in that context? And that's one of the things that we can answer. So I want to thank you for going on the little journey with me into the landscape of quantum field theories, and where in particular we've seen how particle physics with gluon scattering amplitudes, things that are directly measurable at the LHC, map in some setting with a certain kernel into the amplitudes that can be relevant for computing effective potentials for gravitational spirals and gravitational waves. So happy to now hear more questions as we go.
Thank you, Henriette. This was great. I'm sure my clapping mimics what the rest of the attendees are feeling, but cannot transmit right now. Yeah, we have time for questions. If you want to